In the last lecture, I introduced the concept of reliability of a system at a given time t. So, if t is a random variable which denotes the life of a system, then probability that the system is functioning at time t is equal to probability of t greater than small t, and we denote it by capital RT, that is the survival function or the reliability function of the system at a given time t. So, by the definition of the cumulative distribution function, RT is equal to 1 minus FT. So, this reliability function is quite important in the study of lives of mechanical systems, in electronic systems. That means, in engineering sciences, wherever we are dealing with the various kind of instruments, equipments, etc., we are interested in the survival probability. So, we further introduced a concept called instantaneous failure rate of a system at time t, which I called hazard rate at time t, which is the probability of the system failing within a short time immediately after time t. So, the rate of failure. So, we divided by h and we calculated the expression for that, and it turns out to be the density function divided by the reliability function, or the density function divided by 1 minus the cumulative distribution function of the system. And there is an inverse relationship also, which we showed, that the reliability of the system is equal to a constant times e to the power minus integral of h t dt, where the constant has to be determined from the initial condition. So, now we will show that this reliability function uniquely determines the distribution uniquely determines the reliability function, introduces the, or you can say uniquely determines the hazard rate uniquely determines the reliability function, etc. Notice here one thing, that we are dealing with the continuous distributions, because we are talking about the lives of the systems. Although the reliability concept can be determined for probability of x greater than x, can be determined for any discrete distribution also, but right now we are concentrating on this one. So, here let us consider, say, the distribution, let x be the Weibull distribution. With parameters alpha beta. So, we have the density function as alpha beta x to the power beta minus 1 e to the power minus alpha x to the power beta, where x is positive and alpha and beta are positive parameters. The density is 0 for x less than or equal to 0. Now, for this we calculated the reliability function to be, we firstly calculated the cumulative distribution function, which was equal to one minus e to the power minus alpha x to the power beta. Therefore, if we write down the reliability function, it is equal to e to the power minus alpha t to the power beta for t greater than 0, and it is 1 for t less than or equal to 0. So, if we calculate the hazard rate for this is equal to f t divided by r t. So, when you take the ratio, we are left with alpha beta t to the power beta minus 1. Notice here that beta, if it is taking a positive integral value, then this is a polynomial function. On the other hand, if beta is a fraction, then suppose beta is a number less than 1, then it will become an increasing hazard rate as t increases. If we are given h t is equal to this, then we can use the formula for the calculation of reliability from here in the following way. Given ht is equal to alpha beta t to the power beta minus 1, rt is equal to k e to the power minus integral ht dt, that is equal to k times e to the power minus integral alpha beta t to the power beta minus 1, that is equal to k times e to the power minus alpha beta t to the power beta. So, if I put say r 0 is equal to 1, then this will give us k is equal to 1. So, f t will become equal to 1 minus e to the power minus alpha beta t to the power beta for t greater than 0 and 0 for t less than or equal to 0. So, the density function is equal to alpha beta t to the power beta minus 1 e to the power minus alpha, this will be e to the power minus alpha t to the power beta, which is nothing but the probability density function of the Weibull distribution. So, this discussion shows that for Weibull distribution, the form of the hazard rate is of a polynomial type of function alpha beta t to the power beta minus 1. Of course, it will depend upon what are the values of beta, whether beta is a real value or it is a positive integral value, etc. But one thing is clear, if beta is greater than 1, then this will be increasing with t, and if beta is less than 1, then this will be decreasing with t. So, you can have systems where the hazard rate may be increasing with time or it may be decreasing with time. For example, you consider a very new system. Now, we know that a very new system generally it is likely to fail more, but once it is in operation, for example, a new car or a new computer, but after certain time it will work. Once it has stabilized, the life will be more. However, after again a certain stage, the life may start decreasing. Let us consider the special case here, beta is equal to 1 in the Weibull distribution, which was corresponding to the exponential distribution. If we take beta is equal to 1 in the hazard rate, this becomes simply alpha, that is a constant. Now, this is interesting. In the case of exponential distribution, for exponential distribution, that is, if I am taking say f x is equal to lambda e to the power minus lambda x, the hazard rate is equal to lambda e to the power minus lambda x, the reliability function was e to the power minus lambda x, that cancels out, which is lambda for all x. That means, the hazard rate function, let us put t here in place of x, hazard rate function of the exponential distribution is independent of the time, that means constant failure rate. Now, this is the point which I wanted to emphasize earlier when we were talking about the memoryless property of a exponential distribution. That means, if a system is functioning, it has not failed, then the failure rate remains the same. So, that is why the systems which are having exponential life are more stable in nature, and they are good basically for the users. On the other hand, if the ht is given to be lambda, we can calculate using this formula. So, we will get the k e to the power minus lambda t, and k will again become 1 by using the initial condition r 0 is equal to 1. So, it becomes lambda e to the power minus lambda t as the density function. We also discuss the reliability of complex systems. Many times the entire system is made up of several components which may be connected in parallel or in a series. So, let us consider the reliability of such systems. Let us consider reliability of a series system. So, suppose we have say k components with say lives x1, x2, xk, and they are connected in a series. That means the entire system will work if and only if all the components are working. So let x1, x2, xk denote the lives of k independent components of a system with, say, life x. So the reliability of the entire system, that is RT, is equal to probability of x greater than t. However, the system will be working if and only if each of the components x1, x2, xk are working at time t. That means this is equal to probability of x1 greater than t, x2 greater than t, and so on, xk greater than t. We are assuming that the components are working independently, therefore the probability of the simultaneous occurrence will be equal to the product of the probabilities. Now this is nothing but the reliability of the Rth system, Ith system. So what we get here is that the reliability of a compound system which consists of several components connected in a series is equal to the product of the reliabilities of the individual components. In a similar way, we may have systems which are connected in parallel. Let us look at reliability of a parallel system. So there are several links from, say, A to B, and the system will function if any one of the components is functioning. Let us call the lives as x1, x2, xk, etc. Suppose a system consists of k components connected in parallel. So let x denote the system life and x1, x2, xk denote the lives of components. Once again, assume that the component lives are independent. Component lives are independent. Now, if we consider the reliability of the entire system at time t, now this will function if any of the systems is functioning. So we can write it as 1 minus probability of x less than or equal to t. That means the system fails before time t. Now the system will fail before time t if each of the components fails. That means it is equal to probability of x1 less than or equal to t, x2 less than or equal to t, and xk less than or equal to t. This is equal to 1 minus. Now once again we can make use of the independence of the lives of the individual components. So it becomes product of the probabilities xi less than or equal to t, which is nothing but 1 minus probability 1 minus probability of xi greater than t. Now, this is nothing but the Ri. Therefore, the reliability of a system consisting of parallel components is expressed in terms of Rxt is equal to 1 minus product of the reliabilities of the individual. Sorry, this is 1 minus. So, this is wrong expression, 1 minus Ri t. Let us look at one application. The lung cancer failure rate, that is hazard rate, of a T-year-old male smoker is given by ZT is equal to 0.027 plus 0.00025 T minus 40 square for T greater than or equal to 40. Assuming that a 40-year-old male smoker survives all other hazards derive the density function of the life. Find the probability that he survives to age 50. If he survives to age 50, what is the probability that he will survive till age 60? So, this is a shifted Weibull distribution kind of thing, because in the Weibull distribution we have seen the hazard rate function is given by alpha beta t to the power beta minus 1. That means starting from time 0. Now, if you compare it with this, here it is shifted. So, t minus 40. So, we are assuming that the person is already 40 years old. After that, the hazard rate function is given by this. So, from here you can make out that the distribution of the life of the T-year-old male smoker is given by a Weibull distribution. So, we can make use of the relationship between the reliability function and the hazard rate function to calculate the reliability function, hence the cumulative distribution function, and hence the probability density function of the life. So, consider here RT. RT is equal to e to the power minus ZS ds. Now, here we have written indefinite integral there, but here since it is already given, so we can put the limit as 40 to t, that is equal to e to the power minus 0.027 t minus 40 plus 0.00025 by 3 t minus 40 cube. So, one question was asked, find the probability that he survives to age 50. That means the reliability at t is equal to 50. So, once we have the reliability function, we can calculate R50, which is obtained by substituting t is equal to 50 here. So, after evaluation it turns out to be e to the power minus 0.3533, which is approximately 0.702343. That means, if he is a smoker and he is already 40 years old, the probability of his surviving beyond 50 is only 70%. That means 30% the chances that he will not be able to survive. If we are looking at, if he survives to age 50, what is the probability that he will survive till age 60? This is conditional probability that he is having life up to 60, at least up to 60, given that he has survived till 50. So, if we consider this event as A and this event as B, then it is probability of A intersection B divided by probability of B, and that is equal to probability x greater than 60 divided by probability x greater than 50, which is the ratio of the reliabilities at t is equal to 60 and 50, and after some simple evaluation this turns out to be 0.426, which means that if he has survived till age 50, then the probability of his surviving till age 60 is 0.4. If you see here, the probability of surviving till age 50 is 0.7, but if he has survived till 50, then probability of surviving till 60 is 0.42. The probability the density function of the life can be obtained simply by looking at the derivative of the reliability function, because the reliability function is 1 minus the cumulative distribution function. So, the density function is obtained as minus d by dt of RT, which is equal to 0.027 plus 0.00025 t minus 40 square e to the power minus 0.027 t minus 40 plus 0.00025 by 3 t minus 40 cube, that is t is greater than 40, which is nothing but the probability density function of a shifted Weibull distribution. Let us consider one more example here. A system consists of several components as shown below. So, the numbers, this represent the reliability of the component to be functioning. So, 0.99 is the reliability of component 1 to be functioning, 0.95 for the second one. So, this second assembly here is consisting of two components connected in parallel. So, the system, this particular component will be working provided any of them is working. Let us name it 2 and 3. The next part consists of 3 components connected in parallel with the reliability is 0.96 for component 4, 0.92 for component 5 and 0.85 for component 6. The next one consists of a single component 0.95 and the next one consists of a single component. Suppose this is A, this is B. So, the entire assembly is consisting of A to B, 8 components out of which some of them are connected in parallel and some of them are connected in the series. Let us name these systems as say 1, let me call it system life as x1, this system life as x2, this system life as x3, this as x4, this as x5. So, if we are interested to calculate the reliability of the entire system, now this is a series. So, it will be the reliability of the xith system, I is equal to 1 to 5, 1, 2, 3, 4, 5 systems which are connected in parallel. So, this one will become equal to R x1 t. Now, R x2 t is again a compound system. It consists of two parts connected in parallel. The probability that the system is functioning or the reliability of this is given by the formula for the reliability of a parallel system, 1 minus product of 1 minus of the reliabilities. So, if we use this one, the reliability of the second system will be equal to 1 minus, let me firstly write R x2 t, R x3 t, R x4 t and R x5 t, where R x1 t is given by this number, R x4 is given by this number, R x5 is given by this number. If we look at R x2 t, it is equal to 1 minus 0.95 into 1 minus 0.95, which is equal to 0.9975. Similarly, if we consider the reliability of the third system, that is R x3, that is equal to 1 minus 0.96, 1 minus 0.92, 1 minus 0.85, which is equal to 0.99952. If we substitute these values in this formula, we get 0.7689. This shows that the reliability of a complex system can be calculated by using the formula for the reliabilities of the individual systems which are connected either in parallel or connected in a series form. One more thing we should notice here, the reliabilities of the individual systems are quite high, for example 0.99, 0.95, 0.95, 0.82, etc. But if we are looking at the reliability of the compound system, it is 0.7689, which is much smaller, which shows that when we multiply the probabilities, they become smaller because each of the number is less than the one, that is the effect. So, although individual systems may have high reliability, but when we connect them in a say series system, the reliability will become much smaller. If we connect them in a parallel, the reliability will increase because any of them working will ensure that the system is functioning. A system consists of two independent components connected in series. The lifespan of the first component follows a Weibull distribution with alpha is equal to 0.006 and beta is equal to 0.5. The second component has a lifespan that follows the exponential distribution with mean 25,000. The measure is, the unit is hours. Find the reliability of the system at 2500 hours. Find the probability that the system will fail before 2000 hours if the two components are connected in parallel. What is the system reliability at 2500 hours? So, here the two independent components are connected in the series. Let us call this as x1 and this as x2. The first one, x1 has a Weibull distribution. So, the density of is equal to alpha beta x to the power beta minus 1 e to the power minus alpha x to the power beta, where alpha and beta are given here. So, if we look at the reliability function of x1, that is equal to e to the power minus alpha t to the power beta, that is e to the power minus 0.006 t to the power 0.5. If we look at the second component, that is exponential distribution with mean 25,000. So, the density function will be, because mean of the exponential distribution with density lambda e to the power minus lambda x is 1 by lambda. So, if we are saying mean is 1 by 25,000, so the density function will become 1 by 25,000 e to the power minus this. So, the reliability of this is equal to e to the power minus t by 25,000. Now, we are interested in the reliability of the system at 2500 hours. So, the system life, suppose it is x. So, the system reliability at time t, that is equal to, for a series system it is the product of the individual reliabilities. So, this is equal to e to the power minus 0.006 t to the power 0.5 into e to the power minus t by 25,000. So, if we are calculating the system reliability at 2500 hours at t is equal to 2500, then this will be equal to, after substitution, this value is evaluated to be e to the power minus 0.3 and this one will become e to the power minus 0.1, that is equal to the power minus 0.4, which is approximately 0.67. So, reliability of the compound system which is connected in a, which consists of two components connected in a series, can be evaluated by multiplying out the reliabilities of the individual components at the given time. Now, the next part of it is, what is the probability that the system fails before time 2000 hours. That means, what is the probability that x is less than 2000. Now, this can be written as 1 minus probability that x is working at 2000 hours. Once again it is the product of the reliabilities at 2000 hours. So, this we can substitute the values 1 minus e to the power minus 0.006, 2000 to the power half e to the power minus 2000 divided by 25,000. So, after some simplification this value turns out to be this value is approximately 0.98. In the third part, if the two components are connected in parallel, what is the reliability? Now, if the components are connected in parallel, then we have seen that the reliability of the system is given by 1 minus the reliability of x1 into 1 minus reliability of x2. So, if we are calculating at 2500 hours, then after substitution of the values of Rx1 and Rx2, which we have evaluated here, the Rx1 is this and Rx2 is this. Here if we put t is equal to 2500 and substitute in this one, it turns out to be approximately 0.98. Compare the values which we calculated in the two parts. If the components are connected in series, the system reliability is only 0.67 at time 2500 hours, whereas if they are connected in parallel, the system reliability is pretty high, that is 0.98. So, this is the difference, because if we are insisting that each of the components should work, then the probability becomes smaller. When we are having the relaxation that if any of the system is working, then the probability of system functioning will be much higher. That is why in the industries generally there are systems kept as redundant. So, of course, that is part of the reliability studies. When we study k out of n systems, that the system will function if any k out of the n systems are working. So, we find out the probabilities of that kind of events. The next one is the discussion about a beta distribution. A continuous random variable x is said to have a beta distribution with parameters say alpha and beta if it has the probability density function given by one by beta alpha beta, where beta denotes the standard beta function x to the power alpha minus 1, 1 minus x to the power beta minus 1 for 0 less than x less than 1, alpha is positive, beta is positive and 0 otherwise. So, obviously, this is called beta distribution because it is consisting of a beta function here. The integral of this will give you beta alpha beta, therefore, the ratio will become 1. The distribution is quite useful in describing various kind of phenomena where the range is bounded, and if range is bounded we can limit it to the interval 0 to 1. In fact, we can look at the shape of the curves. If I take alpha is equal to 1 and beta is equal to 1, it is reducing to uniform distribution. So, 0 to 1, if alpha is 1, beta is equal to 1. If we are having alpha beta both are less than 1, then it is becoming a function like this. suppose I take alpha and beta equal but less than 1. If we consider say beta is equal to 1, then this term will not be there, and suppose I take alpha to be less than 1, then this will be a decreasing function. Suppose I consider alpha to be less than 1 and say beta equal to 1. On the other hand, if I take alpha is equal to 1 and beta to be less than 1, then it will become like this. If we take alpha is equal to beta but greater than 1, then the shape will become something like this. If we are having say 1 less than alpha less than beta, then the shape will be something like this. The shape will be something like this if we take 1 less than beta less than alpha. So, here you can see that since here two parameters alpha and beta are there, depending upon the values of alpha and beta, various kind of shapes are coming. If you are having alpha beta equal to 1, which is reducing it to uniform distribution, which is a symmetric distribution. If we have alpha is equal to beta but less than 1, then it is having a convex shape. If we are having alpha and beta equal but greater than 1, then it is having a concave shape. It may be positively skewed or negatively skewed depending upon various combinations of alpha and beta values. We can look at the moments of this distribution. Since it is over a finite range, it is clear that the moments of all orders will exist. If we consider say expectation of x to the power k, this is equal to integral x to the power k 1 by beta alpha beta x to the power alpha minus 1 1 minus x to the power beta minus 1 dx from 0 to 1. So, this is nothing but the beta function alpha plus k beta divided by beta alpha beta. So, this can be simplified and we get the expression as alpha plus k minus 1, alpha plus k minus 2 and so on up to alpha plus 1 alpha divided by alpha plus beta plus k minus 1 alpha plus beta plus k minus 2 and so on alpha plus beta. So, if we calculate the mean of this distribution, it is simply alpha by alpha plus beta. The second moment will become equal to alpha into alpha plus 1 divided by alpha plus beta into alpha plus beta plus 1, and therefore, variance of beta distribution will be equal to alpha beta divided by alpha plus beta square into alpha plus beta plus 1. Of course, the third and fourth moment will decide about the symmetry and the kurtosis of this distribution, and we have already exhibited that it will depend upon the values of alpha and beta. Here we give one derivation of beta distribution based on sampling from a uniform distribution. Let x1, x2, xn be independent uniform 0 1 random variables. Let us consider y are the rth largest in x1, x2, xn. What is the distribution of yr? Now, to consider this, we may consider some point t on the interval 0 to 1. Then any xi may be bigger than t, that means it may be between t to 1 or it may be between 0 to t. So, if we consider ai to be the event that xi is less than or equal to t, and if xi's are independent, then ai's are independent events. So, observing of x1, x2, xn denotes a sequence of Bernoullian trials, because each xi may satisfy a xi less than or equal to t, or it may not satisfy. That means ai may happen or may not happen. And what is probability of ai? That is t, where t is a number between 0 to 1. So 1 minus probability of ai is 1 minus t. So if we are looking at, say, probability of YR is greater than t, it is equivalent to the event that at most r minus 1 of xi's are greater than t. Sorry, it is less than t. So this means this event is equivalent to sigma t to the power k 1 minus t to the power n minus k n c k, k is equal to 0 to r minus 1. So let us analyze this. What I am saying is that if the rth largest is bigger than t, then at most r minus 1 of xi's will be less than or equal to t, because if they are bigger than if r of them are less than or equal to t, then naturally it may happen that the rth largest will also become less than or equal to t. So if we are saying rth largest is greater than t, then at most r minus 1 of the xi's will be less than or equal to t. So now let us consider k of the xi's are less than or equal to t. Then for k of them there is a success, and for the remaining n minus k it is a failure. The success probability is t and the failure probability is 1 minus t. So it becomes like a binomial distribution out of n trials, k successes. So the probability of the k success is n c k t to the power k 1 minus t to the power n minus k. And here we are saying that k may be from 0 to r minus 1. So the cumulative distribution function of YR is then obtained as 1 minus sigma n c k t to the power k 1 minus t to the power n minus k. K is equal to 0 to r minus 1. So the density function of YR can be obtained by differentiation of this term. We will get f YRT is equal to minus d by dt. Now here we have to write down the terms. So it is nc0 t to the power 0 1 minus t to the power n plus nc1 t 1 minus t to the power n minus 1 plus nc2 t square 1 minus t to the power n minus 2 and so on, plus ncn t to the power n. So the derivative of this will give us, so if we consider the derivative, the term by term differentiation will be there. Each of the term is a product of two terms except the first and the last. So in the first one we will get 1 minus t to the power n minus 1, there is a minus sign here, plus nc1. Now derivative of this one will give simply 1 minus t to the power n minus 1, and there is a minus sign, so this will become minus, and then you will have plus nc1 into n minus 1 t 1 minus t to the power n minus 2 minus nc2 into 2 t 1 minus t to the power n minus 2 plus nc2 n minus 2 t square 1 minus t to the power n minus 3 plus ncn n t to the power n minus 1. Again we can observe that the terms are telescopic in nature, that is the first term cancels with the second term. Here if you look at nc1, that is n into n minus 1, here it is n into n minus 1 by 2 into 2, so that is again n into n minus 1. So this again cancels out. So likewise all the terms will cancel each other and we will be left with so here the last term was nc r minus 1 t to the power r minus 1 minus t to the power n minus r. So this we wrote wrongly. Here the last term will give us n c r t to the power r minus 1 minus t to the power n minus r, that is equal to n factorial divided by r minus 1 factorial n minus r factorial t to the power r minus 1 minus t to the power n minus r. This is because the cancellation of all the terms after the n c k into n minus k, and that is same as n c n k plus 1 into k plus 1. This is nothing but the beta distribution with parameters r and n minus r plus 1. So this beta distribution arises in sampling from a uniform distribution with rth, the distribution of the rth largest. Next we introduce a double exponential or Laplace distribution. If we remember the exponential distribution, in the exponential distribution the density was on the right side of the axis. If we consider the density on both the sides of the axis, say this is known as a double exponential distribution. Of course, we may introduce parameters here. We may consider 1 by 2 sigma e to the power minus x minus mu by sigma, where mu is a positive parameter, mu is a real and sigma is a positive parameter. So this is known as a double exponential distribution. The distribution is quite useful in various studies where exponential is restricting to the positive side alone, but if we have some values on the left side also, we may, this distribution finds its use there. If we consider the mean, this is equal to mu, which is obvious because it is a symmetric distribution. If we look at the variance of this, this is 2 sigma square. We may look at the measures of skewness, which will be again 0, and the measures of kurtosis will be dependent on the value of the sigma here. The moment generating function of this distribution will exist, because if we are looking at expectation of e to the power tx, then it is integral of this term into e to the power tx. So it will exist for all values of t. In the next lecture, we will introduce one of the most important distributions in statistics, which is known as the normal distribution, and we will also show why it is important here. So we stop here. Thank you.